platform is yours.
Yeah, thank you. So first of all, I would like to thank the organizing committee for inviting us to giving the opportunity to talk. So my name is Tharindu Ranathunga, and I'm a senior researcher at Nimbus Center, which is located in Ireland. So it is under the Munster Technological University. So we are mainly focused on developing human-centric technological solutions, especially around cyber-physical systems and IoT. So today's topic is on beyond data sharing, enabling federated learning services in data spaces. So this topic is based on one of the data space projects that we are working in Nimbus. So it is mainly funded by the Sustainable Energy Authority in Ireland. So to understand the value of federated learning in today's context, so it is important to understand how the data sharing has evolved over time. So this slide kind of illustrates that evolution from traditional centralized data platforms where there's a single data provider and he's the one who aggregates and all the consumers has to trust that, to data spaces which allow organizations to retain control over their data while still enabling self-sovereign and privacy-preserving data sharing. And now we are moving towards more like a data ecosystems, which are kind of decentralized collaborative environments for scalable cross-sector innovations. So these are mainly enabled by data services, trust frameworks, and decentralized protocols, and so on and so forth. So in this context, data spaces are just more than technical infrastructure. So they are the key building blocks of these larger ecosystems. So CODES is a project that we are working at Nimbus. CODES stands for Collaborative Data Space for Energy Performance. And it started as a data space project, which we consider the manufacturing domain. So the participants of CODES can share data sets as well as machine learning models with each other that can be utilized to improve the energy performance aspects within the companies. So it is kind of domain specific, but the core components of CODES enable multiple stakeholders such as the data owners, AI developers, and service consumers to collaborate with each other without moving their data. So it leverages the IDSA's data space protocol, and we have implemented a minimal viable data space, which is open source. So you can try it out. I have given the GitHub link, so we appreciate your feedbacks, and please use it. So over time, this CODES project has evolved into an infrastructure that can support data ecosystems. So we are not just data, but services can be deployed in a self-sovereign manner. So as the next phase of CODES, we wanted to enable decentralized learning on top of it. So where multiple parties can collaboratively train machine learning models without transferring the raw data. So unlike the previous versions of data spaces, or specifically CODES, participants are not just consuming the data sets or pre-trained machine learning models, but actually actively contributing in the training process. So this is mainly enabled by federated learning. So I hope you have come across this term. So it's nothing but a kind of machine learning technique. So here, instead of moving data to a centralized place, so each participant trained their local model using their own data sets locally, and only the model updates are shared between each other. So each participant can kind of aggregate the model updates and create a global model that have a larger understanding and a like more accurate model. So this technique is kind of important because it supports the privacy-preserving collaboration, ensuring that sensitive data never leaves the source. And on the other hand, it helps the organization to meet the data sovereignty and compliance related issues, especially in critical sectors or regulated sectors such as healthcare and finance, so on and so forth. So it is kind of the ideal solution to extract intelligence in critical sectors where data sharing is restricted. So at the same time, the training is done in a decentralized and distributed setting, so the computation capability can be offloaded. So it is much more scalable than the centralized training, like doing everything on a single server, and so on and so forth. So while this federated learning holds a great promise, so you can say like integrating into or using it in real world, it's kind of complicated or need to think about it thoroughly. Because there are few research challenges that we need to address. So for example, the policy fragmentation. So in here, like each participants can operate on a different geographical area, which they have to comply for different legal frameworks or compliance frameworks. So we need to way to express these different type of policies in a flexible way that reflects each party's obligation. And since the training is done in a distributed manner, the enforcement has to done in distributed setting, which is kind of complex. On the other hand, we need some kind of a trusted and interoperable way of discovering these services if some kind of a provider want to advertise them, and consumers need to kind of search, go through the catalog. So we need to have some kind of a common or interoperable standard in defining these services. And also we have challenges related to sovereignty and control. So even the raw data is not shared, but organization or the participants can have concerns on losing the control of their machine learning models or the software infrastructure that is involved. Finally, FL also introduced some type of new attack vectors that we have to consider, such as the model inversion, poisoning attack, membership inference, to name a few. So in developing federated learning solutions, we first need to address these challenges. So now we have discussed the challenges, so let me introduce how we are addressing them through the Code's FL learning platform. So we use the concepts of data spaces. So data space by design supports sovereign and controlled data sharing. So we leverage this concept so that the service providers can advertise their FL services on top of the data spaces, and also they can orchestrate the software services that need in the training process using these data space concepts. So our platform has two set of components, or two set of features. So on the left-hand side, you can see the features related to data spaces. So these kind of the features that augment the data space, such as the metadata preparation. So as you saw in the last presentation, the identity providing the identity, policy negotiation, and so on and so forth. So these are the features that kind of complement the existing data space features. And on the right-hand side, you can see the actual federated learning specific services that we have implemented. So these involve FL service definitions. So in federated learning, we need to have a server and client, so the orchestration has to be done. So there are components related to orchestration, policy enforcement, and things that improve the observability across the machine learning pipeline. So even though it looks a bit complex and foggy, so if you look under the hood, these are the core technologies that we use. So we are not reinventing the wheel. So instead of we are combining all the available technologies and standards and building the capabilities that are required to support federated learning. So we use the IDSA protocol, as you already might know. So we use the architecture in there, specifically an implementation of a connector called True Connector. So we have given some FL capabilities by implementing a few data apps on the True Connector. And we use Flower Federated Learning Framework. So it is kind of a state-of-the-art framework that is used in industry for federated learning. So which we use to implement custom strategies for model aggregation, and we have introduced a new policy management pipeline into it, and also we have improved the observability aspects as well. And then we are using MLflow, so it is kind of a state-of-the-art platform for tracking the machine learning models. So we have introduced few capabilities to support the semantic interoperability. We have vocabulary or ontology developed, so the machine learning model developers can log their models while developing or while training the model, and so on and so forth. So this is the end-to-end workflow of the system that we have built. So starting from this side, where the FL service provider can do the local deployment of the machine learning model training, and they can advertise the service metadata, more like the data space on the service catalog. And at the same time, he can publish the software components required for the model training on a repository. So the consumers, on the other hand, can go through the service catalog. If they are interested in participating in a model training scenario, they can pick the service and start negotiating the contract using the data space protocol. So if everything goes well, so they can download the software components and deploy at their end and connect to their own data source so they can participate in the model training process. So we have kind of identified few FL-related policies that we need to integrate it into this workflow. For example, fairness and bias mitigation, incentivizing the consumers and all the ones who providing the data or participating in the training process, and the model quality kind of matrices, checking them, which is set by the provider, and so on and so forth. So we have a few APIs so that the provider can use this API to define the policies according to their scenario. So then these policies will be converted into a more common standard called ODRL, Open Digital Right Language, so which is the IDSA specification of policy management. So what you can see is an example of a such policy. So since I do not have much time, so I'm not going to do a demo here. These are a few screenshots. This is from the provider's end. This is how the provider described their FL scenarios, how he defined the policies, how he converted into a resource description, and how they advertise in the service broker, and so on and so forth. So this is an example of a FL session. So you can see the fine-grained, the observability. So there are different, in this case, there are 2 clients involved. You can see the accuracy of the models that they provide and whether they pass the minimal accuracy threshold that is set by the provider in the policies. So this is just a simple example. So to conclude, let's see how we have addressed the challenges that I have mentioned. So we do the policy enforcement end-to-end in the pipeline of the machine learning, from the connector itself to server, client, and orchestrator, so which is kind of outside the IDSS capabilities. So they do at the connector level, and then we give the traceability across the pipeline, which also will helpful in mitigating security attacks. And we provide the semantic and interoperability through ontology that we have developed specified for the federated learning scenarios, and then the data sovereignty and control by using the data space principles. So at Codes, so we believe in a future where there are frictionless service machine learning model training and data sharing, and it doesn't come at a cost of control. So our mission is simple but powerful: own your data, grow with others. So if you're interested in learning more about this platform or collaborating with us in further European calls, so feel free to contact us. Thank you.